in the club meetings we'll see.
Brad. Simon, different people have difference. But Cora was joking. Her signing and our
Where's my mouse? There it is. Look at that.
We're
so fancy.
here. All right.
I'm actually gonna make this slightly smaller.
Okay.
All right, y'all ready to get into it? Let's learn.
Just the forward button.
Okay, one more time.
Oh, I wasn't focused.
All right. So today we're going to go over some techniques in Python that could possibly get you accused of academic dishonesty. These reasons would be because they're either so useful that only an LLM or some random Stack Overflow user could come up with them, or they're so absurd that only an LLM or a Stack Overflow user could come up with them. So disclaimer, obviously, not my fault if you get accused of it, but these aren't anything like secret, super secret tricks. You can find these on Google or in this presentation, but yes, let's go over them. All right, first, a basic one. Operator overloads. Here, we're overloading the addition operator with a class, right? So they have the double underscore method there for add, and that overloads what happens when you actually call the, or when you actually use the, plus operator for this class, right? So you'd think, oh, I can just add the values, but actually I've overwritten it to multiply the values. So this would be an evil class.
So another fun thing you can do in Python that doesn't make a lot of sense is the else statement after loops, where the else statement will only run if the loop exits via a break rather than exiting normally. So in the one on top there, that for loop will not print exited, or it'll print exited with 7. Oh, that's actually wrong. My bad. That should say exited without 7. But it'll only run that print statement if it never breaks, but it's going to break when it is 7. And then the while loop down there it checks if it's running, it does a thing. If the result of the thing is none, then it'll break out. But otherwise it'll do another thing and keep doing that. Is that a question, Rain? Yeah.
I might be wrong.
I think so.
I don't think you can do this.
I've never seen this in another language. So also unpacking. So lists and tuples can be unpacked using multiple assignments. So if we have an array or a tuple here with 3 things in it, we can assign it kind of like this, kind of like that, to allow us to just kind of assign, first thing into A, second thing into B, third thing into C, just with one assignment statement. Except this just applies to any iterable. So like if you have a set which isn't ordered, you can unpack it. It's going to be weird because you're not going to have a defined order to which thing gets put in what variable, but it's a thing you can do. That also applies to dictionaries because dictionaries are iterables as well. You can iterate over their keys. So in this example, the variables hello and world will be assigned the values string hello and string world. Of course, hello might get world and world might get hello because there's no defined order, but it's a thing you can do.
It's just kind of students that are tuples. If you just have 1, 2, 3, it'll allow you to assume that it's a tuple.
Yeah.
That's true.
Clarity, you can.
Yeah. That is true.
So also list comprehensions allow for putting a for loop to construct a list all on one line. So in that top example there, we've got array 1, 2, 3, 4, 5, and then we initialize another array called ret, and then for I in array, we just append the square of I. So a ret is basically just going to end up holding the squares of every number in an array. That could all be done on one line there with I times I for I in array inside the square brackets like that. You can also add kind of a filter here, so then it'll only put in the values over here that match where this statement is true. So this one will only add even numbers, the squares of even numbers to the array. There's also dictionary comprehension, which allows you to build a dictionary in basically the same way. You can iterate over another iterable and construct a dictionary out of it using this sort of notation for key value pairs. You can also nest these comprehensions. So if you have 2 for loops, the outer for loop goes like on the left here, and then the inner one goes on the right, and the actual value you're trying to kind of end goes like all the way to the left. You can also add a filter over to the right here to filter values as well. So
speaking of filter, there's an actual function in Python called filter. It does a similar thing to how Ethan described the like comprehensions with conditions in them, but basically you can define something to filter based on a certain criteria. It's essentially the same thing as the first one there. You don't enter n in numbers if n mod 2 is 0, but it's just a little different way of doing filters. And then we have a lambda here, but we have a little slide going over those too. First, we're going to talk about maps, though. I use this one actually very, very frequently because sometimes you got a list of a bunch of strings and you want to convert them to a bunch of integers. This is particularly useful, like when we're doing a caddis problem. You read it in from standard in, it's going to be read in as a string unless you map them using map, and then the arguments for map are the type that you want to map it to and the iterable that we're mapping. So using that, I convert it back to a list using the list function, and I get a list of all of those integers, or all those strings turned into integers.
Okay, so list comprehensions can also be generator comprehensions if you put them in parentheses. And the difference between that being list comprehensions will actually go and fill out an entire list and then return it, whereas generator comprehensions will kind of lazily iterate as you actually need the values from it. So if you have a really big long array of stuff that you don't want to pre-process, then you can use a generator comprehension to only actually calculate the values as you need them. So, and also if a generator comprehension is the only argument to a function, you can just put it, you don't need the parentheses around it, you can just put it in kind of that first layer. So some of these examples here, like ::.join will just create a string out of whatever iterable you give it. And if you give it a generator comprehension like this, this will convert an array of like character integers that correspond to character codes into an actual string. Same with over here, this will sum up the square of every number in an array. This one will return true if every number in a list is even using all, which just takes an iterable of booleans and then returns true or false depending on whether they're all true, some are false. Then you can also, this one checks if a number is prime. These top three were actually ones I used at the competition we went to last weekend. Those three were all like integral parts of the script. And then this last one here I made for fun while I was making this presentation. So
speaking of generators, we can actually make like a self-defined function become a generator. Instead of using the return keyword to give what you want to return, you can use the yield keyword, which basically repeatedly yields the different outcomes of this. So instead of just returning A, I yield it, and then I can iterate through that generator. So this becomes a generator, which I turn into a list, which means that it gets all the values from that generator. But if I wanted to, I could get them one by one just by looping through that generator call. And then, like I talked about, we have lambdas. So lambdas are actually pretty useful. You can basically define a one-line function that just does something simple, right? I mean, you can do more complicated stuff like I'll show later, but this is something pretty simple. Instead of having something that I've defined called square of x, I have a square lambda where it does the exact same thing, but it's just in one line right there. And so for this one, the square and square lambda are going to be the exact same thing because it's the same function. And they're particularly useful, like I showed earlier, if I want to like map something to a bunch of, map an entire iterable to something else, right? So in this case, I'm giving it nums, which is some integer or some array of integers, and I'm mapping those to their squares using the map in the lambda. So yeah, a use case for a lambda. Say I'm trying to sort something, but it's like a list of tuples here, right? So it's not going to know what to do with that unless you give it a specified key. So using the optional parameter key in the sorted function, I'm passing in a lambda, and the lambda just gives it the first item, so the one index, the second item in each lambda. So it's going to sort based on that 3, 4, and 5. So yeah, that's how you could use the lambda with sorting something. So now I'm going to go over some data structures that we learn about the ideas of them, but we don't actually know how to do them in Python unless you have actually looked these up. But these are something that I used in that competition we talked about last week, or just use very regularly for simple stuff. Well, complicated stuff behind the scenes, but pretty simple to implement, right? So first I'm going to talk about default dict and counter. So a default dict is a dictionary, but it acts a little differently when you try to access a key that is not already in it. So when I create an instance of the default dictionary, I give it a type. And when I give it that type, if it tries to access a key that is not already in the dictionary, it gives it a default value associated with that type. So I have a DD, which is my default dictionary, with a type int. And there I'm accessing a key that's not in it, right? Because there's no keys in it. And what it's going to do is create a key based on the key I've given it to check, and create it with a default value of 0 for an integer. And then it's going to add 1 to that. So now it's a dictionary containing a map from key apple to the number 1. And then similarly with counter, it's also in the collections module. And with that, you can just pass in some sort of iterable. So in this case, I'm passing in a string. I could pass in a list. I could pass in any other iterables we've talked about, and it will count the occurrences of different items in that iterable. So in this case, it's counting the letters. It's taking apart that string and counting the number of occurrences of the letters, right? So once it does that, I can print out, just like a dictionary, count of L is going to be 2 because there's 2 L's in that iterable that I gave it. So that's something, both of these I used in our competition. They're super useful and very easy. That's 2 lines and I already got all the stuff I need. So another thing, in data structures, we talk about min-max heaps. Here's how you do it in Python. I usually use the heap queue class because it's super easy to turn some sort of like iterable that I need into a heap just by using the heapify command here. So using the heapify function, I pass in my data, which is originally just a list, but it turns it to a heap that I can actually pop from. So in this case, it's going to pop from it. And by default, it's a min heap. So what it's going to pop is 1 because that's the minimum value when I heapify that. You can define it as a max heap. It takes a little bit of extra effort. Usually what I do to define a max heap is just go through the iterable and multiply them all by -1. Not the greatest way to do it, but it ends up working out. And then when you print out, you just have to multiply by -1 again, keep track of that. But there's probably a better way to do it, but that's how I do it.
You don't really know what the difference is between a generator and iterable.
So generators are like a specific class of iterable associated with like some code. Usually, like when you define a generator, you either make a function that has the yield keyword in it instead of return, or you have a generator comprehension. Whereas an iterator and iterables are like general classes of things that you can, they hold multiple values. Like a list is an iterable, and then a tuple is an iterable. Sets are iterables, dictionaries are iterables, generators are iterables. So it's kind of like a subclass of a generic.
You can do both, but kind of the same way. Yes.
Yeah.
Yep.
And there is technically like a difference between iterator and iterable, Because like an iterator is like an actual specific data type in Python, whereas an iterable is anything that can be coerced into an iterator. I think that's the distinction. Don't quote me on that, but it's something along those lines.
And the last couple ones to talk about for the data structures are going to be DQ and a named tuple. So a DQ, or a double-ended queue, which you could treat as a regular queue like we learned about, if you really wanted to, just only pop from the one side. But you just use the collections class, and you define a double-ended queue with, again, some sort of iterable, and then you can append to either side, left or right. If you just want to treat it as like a regular queue, you can just only append to the left, and in that way you can act as a queue, right? And then one of my favorites is something called a named tuple. So instead of having to define an entire class where I'm mapping attributes to a certain class name, I can just define something called a named tuple with a name and the attributes. And using that, I can define, like, my PT variable here is an instance of the point named tuple with the values of 1 and 2 in that order that I've defined, X and Y. And the important distinction here between this and a class is, one, this is immutable. You can't add different attributes to this once you've already done it, because it's a tuple and tuples are immutable. And secondly, this is not going to work if you want to use like a method on the class or anything like that. It has to just be attributes. So it's perfect for something like I'm showing an XY coordinate plane and I'm storing the point, right? But it wouldn't work if I wanted to actually do anything with that point other than, you know, defining my own function on it outside of that. So this is something to consider with that. But I use those not super regularly, but I've used them, and it's really just a way to make things more Pythonic by using names of stuff. But yeah. So these next ones are, I use a lot less frequently, but these are still technically things that you can do. I wouldn't recommend using the second one here, but
Yeah, this is going more from the advanced technique to the like cursed techniques.
I actually have solved a few Caddis problems using this eval thing. So the eval, it evaluates the mathematical output of an expression that you give it in a string, right? So in this case, my string to eval is 2 asterisk 10, so 2 times 10, and it's going to evaluate that exactly how Python would evaluate some sort of mathematical expression like that, and it's going to give me 20. And that is something I've used before, like you have some sort of problem where you're given these numbers and these operations, find all the things I can do to, you know, get the number 15 or whatever. And so you can just loop through all of them, right, and check all their evals. The second one here, I've never used in an actual like problem solving thing, but I guess you could probably use it for something weird. But you can dynamically execute a piece of code using the exec call. So you give it a string of Python code, and then you call exec and it runs it. And so when you do that, it's going to print hello from exec. Again, not exactly sure why you would do that, but it is something you could do.
Yeah, it's also worth noting that both of these functions are massive security risks, and if you ever put them in an application, then you should be fired from your job immediately. Also, eval doesn't just evaluate expressions, it can also parse like data types. Literally any, just like
Any-
Python syntax.
Yep.
Can be, it'll parse, both of them will. Eval will actually return the value of the expression.
So
So does it use like
As Python code.
yeah.
So yeah, you can there's way back in the day when I was writing my first Python scripts, I didn't know what JSON was yet, so my idea to save and load data was to print a dictionary out to the console, copy paste it into a text file, then read the text file back in and eval the dictionary.
That's good.
So yeah, like Ethan said, massive security risk, but if you need to solve a Caddis problem, it doesn't matter.
Yeah, I mean, whose computer is it gonna hit? Not yours.
All right, now we're getting into the really stupid stuff that you probably should never ever do. This is going to be a recursive lambda. So lambdas, like we showed earlier, are functions that are defined like in one line, right? And you can pass in a function as the argument for that lambda. So that's what I'm doing here. So the outer function is accepting the function that's the second lambda, and then the inner lambda is actually doing the recursion in that step right there where it x times f of x and then x minus 1. So it's calling itself again, and it allows it to call itself recursively. I would never use this. It's something you can do.
Yeah, it's also worth noting that this is how you do actual recursion in lambda calculus. Like that's just actually how you're supposed to do it. Granted, lambda calculus also doesn't have numbers in the traditional sense, so there's a lot of best practices that kind of go out the window when you don't have numbers. But
Yeah, that is something you can do.
Yeah.
I wouldn't recommend it. Yeah, it's really weird, but it's cool.
Reminds me of some stuff I've done in Unix.
functional programming.
So
I don't know how to use it.
this one
Yeah, config works.
is a little less weird. I actually have used this before. They're kind of cool. They're called decorators. If you've ever implemented something and you wanted to cache it, you could use like from the functools library, there's an LRU cache decorator that automatically caches the output of a function. In this case, my evil decorator doesn't actually do anything useful other than printing something before execution, then executing it, then printing something after execution. It isn't really doing that much, but you can define an actual wrapper and using the @ symbol, tell it to every time you call this function read, it's going to actually call the wrapper and then do something in there. This wrapper is going to return it's going to return a function, and it accepts a function as the argument, right? So yeah, it's it'll work for any kind of function. You can write your own and do something really weird. In general, the only time you'd use some sort of decorator is to add extra functionality to a function, but avoid changing the actual code of the function. Just maybe you want to do some testing or something like that. That would be helpful for that. But
Yeah, these decorators also get used a lot for like HTTP routing stuff. Like Flask uses them. AIO HTTP has a thing for them. Fast API, I'm pretty sure uses them. So that's like they do these. This is probably the one thing in this section of the presentation that has a lot of legitimate use.
yeah, so then we're getting really into the stupid stuff. This is, cursed, and in general, that's probably not needed as a precursor. They're not useful, but yeah, we have a few final ones that are definitely. So, you can have meta classes and tell it to add an attribute to a class, but not actually adding an attribute the normal way. You can tell it to add a special attribute using this this double under method new. Allows you to pass in, reference to the self, a name of the class that's being created, the base classes, and a dictionary of the attributes and methods. So in this one, I'm defining an attribute of that dictionary called added attribute. I'm calling it mystery. And then using that, I'm calling the new, and then this new subclass is going to have that added attribute, even though you've never actually added it, right? So I don't know why you'd use this, but it's cool because that's how the Python, the double under new method works. So you can pass in your own dictionary of attributes to values. This is called
Monkey patching.
if I remember it correctly. And using this, you can actually change during the actual running of the program, change what different functions do, right? So I'm importing the math. I'm saving the original math.square-root function in something called original square root. And then I'm redefining it to be a lambda function called a cheated square root. And what it's going to do is return the string cheated square root. And then once I print the square root of 16, it's going to call that lambda function. And then it's going to, return that cheated square root string. And then at the end here, it's going to, put it back in place, right? So that just gives us our original square root function. Yep, that's something you can do.
Yeah, and this one isn't useful in like proper software development, but it is actually useful when you're trying to like deobfuscate scripts, particularly like JavaScript. if something ever like prompts for input or calls a specific function like from the API that you know it's going to call, you can monkey patch that function to say call a debugger statement and force a breakpoint where there's not supposed to be a breakpoint, which can make debugging and deobfuscating like infinitely easier.
This one is there's a module called inspect, which allows you to actually get the source code of a function. Kind of interesting. There's probably a use for it that I don't see, but in this case, what it's going to do is literally print out the def sample function AB return A plus B. It's going to print out the source code of the function that I give it. So yeah, there's probably some use case for this. Otherwise, it wouldn't be there. But
Yeah.
I've never found one.
Python also has a disassembly module that allows you to get the actual Python bytecode of a function, similar to how inspect lets you get the source, which also isn't particularly useful, but it can be neat to look at generated bytecode of Python functions. So yeah, it's not useful until you have to reverse engineer Python bytecode back into source. Yeah.
So, in conclusion, Python is pretty powerful, but it's also weird. You can use all of the super cool techniques we learned today the next time you have to code a Python assignment. And you can say, hey, I learned about how you can do a nested generator comprehension. And then you can, you learned it. You actually know it. It's not an LLM generating some sort of weird code for you.
Didn't even talk about.
They had so much to talk about.
Talk about a bunch of like.
Yeah, that's what I'm.
Yeah.
I mean, we talked about
I talked about
like
new.
overloading and
Yeah.
whatnot new. Like really, most of the Dunder methods are the same. You just assign a function to it and hook something.
Yep.
Yeah, I use repr quite a bit, where it is for just the human representation of it.
Yep. Yeah, so when I showed that operator overloading with adding, you can do that with basically every operator, right? You can, if you call the string conversion on something, you can give it something else. Right? So it just defines how the class reacts when you do something to it. So
Yeah.
that is something you can do. I didn't want to go over each of those individually because it would have just been a lot of the same exact thing. But yeah.
Yeah, there's also with like map and filter and whatnot, those actually take callables and not types, so you can pass both like lambdas or an actual class constructor to them. Same with default dict. It just takes a callable that returns a value. So you could have in a lambda that returns 7 if you want every value in your thing to be 7. So yeah.
Any questions on any of these cool techniques? I can go back to any of the slides if there was any confusion on how to do any of them. No? Cool.
Well, thank you for coming.
Thank you very much. Hope you learned something.